The second application for the total cost model is to identify the design that minimizes our total cost. And design means in terms of the capacity, okay, how many servers. In order to recognize the approach that we're going to follow in order to do that, let's see the relationship between the total cost and the capacity, the service capacity. Remember from the previous formula of total cost, it consists of two components, right? The first component is the service capacity, which was CS times M. So if I'm showing the service capacity on the horizontal line, that means the cost will be linear, right? Because it's CS times M, CS is constant, so it's of the form Y equal AX. While the second component is cost of customers waiting, which is CS times LS. But remember the formula for LS, it's LQ over lambda, and LQ is a very complex formula which will result in a shape like that for the cost. It's exponentially decreasing with the capacity. But we are interested to minimize the total cost. So we sum up these two costs and we get the curve for the total cost. And if we have that graphically, then we can find the optimal capacity, right? Because we can then locate the minimum cost on the cost curve, and we can project it to hit the horizontal axis, and this will be our optimum capacity. However, we're not going to solve that problem graphically. We need a quantitative or methods to use. And this is what we're going to see in the next slide. All right, so what do we learn from the total cost curve? In fact, the shape or the characteristics of this curve will help us come out with a procedure to find the optimum capacity. Okay, what do we notice here? We notice that the total cost decreases, all right, and then it reaches a point which is minimum and which corresponds to the optimum capacity. And from this point onwards, it increases again, right? This will give us an idea about what to do to find the optimum capacity with calculations. So this is what we're going to do. We start with an initial capacity. Okay, and we calculate its corresponding total cost. For example, you start with, let's say, M equal to 1, right, as an initial capacity. And you find the total cost, as we did in the previous example. It's CS times M plus CW times LS. Then, from the first, of course, step, you cannot come up with a conclusion. You have to do at least a second one. So now we increase the number of servers 1 unit at a time. So the next will be M equal 2. Okay, and you find also its total cost. Now, then you compare the total cost for M equal 2 with total cost for M equal 1. If you found out that the total cost decreases, that means you know that you are on the left-hand side of this curve, okay, where the cost is decreasing. So you continue. And we also make an increment of 1. Now we find also the next total cost. When you find that the total cost of an increment or a capacity has increased, then you stop. Why? Because you know that you have already crossed this point. And then you choose the capacity that you just calculated or that you calculated one step before that. All right, so we're going to apply this procedure in the next example, example 5, and it will be very clear for you. Okay, so as an application for the design problem, so we are here responsible to find the optimum capacity. We are given the following, that trucks arrive at a warehouse at an average rate of 12 per hour. And then these trucks have to be offloaded. And there's a crew of 5 workers who is offloading or unloading these trucks. And they can do that in 7.5 minutes. Very fast. Now, due to some changes, the manager wants to re-evaluate the number of servers. And he collected the following data. A worker is paid $20 per hour, and the truck and the driver cost $120 per hour. All right. So, assuming that number of docks is not a constraint, that means we have enough space, how many workers should the manager employ? To answer this question, how many workers, you should understand one thing, that these 5 workers, they make one server, right? Because the 5 workers together can unload the truck. And what's the service that we are giving here? Unloading the trucks, because this is a loading dock, right? So the 5 workers is a group of 5, and they represent one server. So to answer the question, we should first answer what the optimum M should be. And then we multiply that by 5 to find the number of workers. So what do we have from the given so far? We know that lambda is 12 per hour. That's very clear. Service time is 7.5 minutes, also very clear. From that, now we are familiar with this, how to convert that into mu. It's 8 trucks per hour. And what do we have? We have, now I can calculate the ratio, lambda over mu, to be 1.5. And we have some costs. We have the service cost, CS. 20 is not the service cost, right? Because this is how much I'm paying every worker, but my server consists of 5 workers. That's why my server cost, my unit server cost is 20 times 5 workers. That's $100 per hour. This is how much every server cost me. Then what about the cost of waiting? Who will wait? It's the truck and the driver. And we are given that these cost $120 per hour. So that's our CW. All right, so now we have all the information that will allow us to do the procedure that we have discussed in the previous slide. So let's do it. All right, according to the procedure that we discussed in previous slides, is that we start with an initial capacity and then we find the total cost, right? And then we increase it at the increment of 1, find the total cost, compare the cost, see whether we are decreasing or increasing, and take the decision accordingly. So that's why I prepared now these titles for a table that I'm going to use. Let me go backward to show you why I need each one of these. I need to finish with the total cost, right? To find the total cost, I know it's equal to the service cost plus waiting cost. Service cost is equal to CS times M, and M is my first column. A waiting cost is equal to CS times LS, and that's why for every row I need to find LS. And to find LS, I need to find LQ. Okay, so how to start? The procedure says start with an initial capacity. And you may wonder, isn't initial capacity always equal to 1? No, it's not always the case, right? Look, for example, in this problem that we have on hand. Lambda is 12 and mu is 8. Meaning what? Meaning that demand is 12 and my capacity is 8. So if I have one server only, group 5, one server, my capacity is lower than my demand. So I'm overloaded, so I cannot use the model. So my minimum capacity or my initial capacity is what? It's the minimum capacity that makes my system underloaded. So if I have 2, for example, my system capacity would be 2 times 8 would be 16, greater than lambda. I'm underloaded, then we can use the model. So that this will be my initial capacity, 2, right? Because this is it. It makes my system underloaded. Now, to find LQ, how to do it? We find it from the table. I'm not going to show you again the table because you can see, or you could tell that it's really very simple to look up for these values. But I can tell you that the value would be 1.93. Then LS, how to find LS? Using the basic relationship. It's always equal to LQ plus lambda over mu. Lambda over mu is constant, doesn't change with every row, right? because every row I'm changing m, I'm not changing lambda and mu. So it's always equal in all my calculations. LS is LQ plus 1.5. So in the first row, for m is equal to 2, my LS will be equal to 3.40, which is 1.93 plus 1.5. What about the weighting cost? My fourth column, it's equal to CW times LS. Okay, so it's always equal to 120 times LS. Okay, LS is already found, so multiply that by 120, we get 412. Service cost is very simple. It's equal to the cost per server times the number of servers. In this case, it's 2 times 100, so that's 200. And total cost is very simple. It's the sum of these two, so that's 612. From the first calculation, I can tell nothing, so I have to do at least one more. For m equals 3, remember we increase at increment of 1. We read that also from the table LQ to be 0.24. We do the same calculations and we found the total cost to be equal to 509, always 510. What does it mean? If this is the total cost curve, that means we are still in this area, right? We are still decreasing because 612, okay, it decreased to 509. Now we increase m also by 1. For m equal 4, we find the total cost to be 585, which has increased, which means we have shifted to that area. So we have already crossed the optimum capacity, and that's why we stop, and we say that the optimum capacity for us is 3, and this will be our answer. But to answer the original question, which is how many workers we should hire, it will be 3 times 5 workers, right? Because 3 servers, every server consists of 5 workers. So that's 3 times 5 equal to 15 workers. This is our final answer. All right, so I hope that this is clear for you. This is a very important application for the waiting line where you are doing the design yourself. This is a very powerful tool.